Alright, so it has been a long day, so I'll try to keep it short, and feel free to ask me questions maybe after the talk, or I'll be outside. Thanks Phil, and thanks Jason for the invitation. I'm happy to be here to share what we've built at Twitter. So this work was done jointly with my interns sometime back, Jordan and Owen, and currently with my colleagues Karthik and Salish. So Karthik is the engineering manager of the streaming compute team, and Salish reports to Karthik. Alright, so as we all know, we all live in a connected world, and every so often we receive these reports from Cisco, from Verizon, and Merrymaker from Kleiner Perkins, wherein they give out projections about where the internet is going. So clearly from this, these are some of the highlights from a recent report from Cisco, where they highlight the growth in the number of devices, the growth in the connection speed, and the increasing use of internet around the globe. So one of the key components of increasing use is the real-time nature. And as you all know, that Twitter is known as a real-time communication platform. It is used by in a variety of contexts, from politics, where politicians like Hillary Clinton, the Australian Prime Minister, they flock to Twitter to do Q&A. You report incidents like the plane slide at the LaGuardia airport, the riots in Baltimore, the earthquake in Nepal, and it is also used by players of World of Warcraft. So clearly, to be able to support a real-time communication platform, we need to be able to process these tweets in a streaming fashion. And as some of you may know, that recently Twitter announced our next generation streaming platform called Arun. This platform was developed by Karthik's team. So all the credit goes to Karthik's team. They published a paper in SIGMOD this year, which was presented a couple of weeks back. So I strongly encourage you to have a look at the paper for the details. It's a leap ahead in terms of performance compared to Storm. So Storm has been used at Twitter for a long time. We open sourced it, and due to the performance limitations of Storm, the team developed Heron, and as I mentioned here on the slide, there are significant performance improvements by using Heron. And all the topologies have already been migrated from Storm to Heron at Twitter. So here is an example of a topology in production in Heron. As you can see, that there are multiple boards, and you have a single spout, multiple boards, and typically each topology has multiple hosts. Each host has multiple instances, and we monitor many metrics per instance. So this is an example of the various topologies. It can be as simple as 2 spouts and 2 boards, and what you see on the bottom right is a very complex topology with tens of different instances, and each tens of different hosts, and each host having multiple instances. So to be able to deliver real-time experience, you need a streaming processing framework. The other component is that you need to have very high data fidelity. So, and the reason is multifold. Just like any other internet company, at Twitter also we make the decision-driven is data-driven. We run hundreds of A/B tests on a regular basis. We also need to support our data partners like Nielsen and Data Miner. So data fidelity is extremely important. And last but not the least, the topic of interest to this audience is the operational nature, that we need to ensure that we are highly performant and we are highly available. So what are the different challenges when it comes to data fidelity? Well, there are multiple of them, anomalies being one of them, and this is what I'll be focusing in this talk. So broadly speaking, you can classify the source of anomalies into two categories. One is the exogenic factors, which can manifest themselves as anomalies in user behavior, events. You can classify events in two categories: planned events such as the Super Bowl or Christmas, or unplanned events such as the blackout during the Super Bowl a couple of years back. And then there may be anomalies in infrastructure data. The temperature in your data center may go up, and which may result in anomalies. The other category is the endogenic factors, where due to agile development and due to multiple A/B tests, you may observe anomalies in your application metrics or business metrics. And last but not the least, the other challenges is, as is true for any big company like Twitter, that we monitor millions of time series. So how do you scale in the sense that how do you monitor and detect anomalies in millions of time series? So there are a variety of potential causes which may induce anomalies. For example, spike in input traffic. You may have a hotkey problem, or you may have connectivity issues, such as, like in context of Heron, you may not be able to connect to Manhattan, which is an in-house data store developed at Twitter. You may not be able to connect to Kafka or to Kestrel, or even otherwise, you may not be able to connect to other containers in the same topology. And so some of the other potential causes include software issues, like you may have memory leak, and last but not the least, you may have anomalous nodes, which may manifest themselves either as slow nodes, which we often see in large clusters we have at Twitter. It can be a data store, or it can be a large Hadoop cluster, where slow nodes often are a big pain point for the SREs. And the other flavor of anomalous nodes is that the node may actually die. So how do you detect these anomalous nodes automatically in large clusters? So in the context of Heron, one of the common symptoms is that you may experience a spike in the Kafka lag, and this impacts the real-time processing of business metrics such as tweets and retweets, and which directly impacts our data partners such as Nielsen and Dataminr. Some of the causes of increase in the Kafka lag is the increasing back pressure, as illustrated here on the plot. It can be due to failures that your writes to your data stores may slow down, or you may experience connectivity issues, and then you may experience container deaths, in a new concept introduced in Heron, which was not there in Storm. Now, as some of the speakers have already mentioned, that at large scale, where you monitor thousands or millions of metrics, visual detection of anomalies is just not practical. It is prone to error, and is just not scalable. So in light of this, we and my interns and we started to work on an algorithmic approach on how to detect anomalies in business metrics as well as operational metrics. So historically, the topic of anomaly detection has been researched for over 50 years, from statistics to econometrics, finance, signal processing, e-commerce, network intrusion, and of course operations. So what I mentioned here is on the slide are the two common statistical tests which have been used extensively. They were proposed almost 30 years back. The limitations here are mentioned on the slide. First of all, they assume that the underlying distribution of the data is normal. The graph stress is good for only detecting one anomaly. But this can be circumvented by using the ESD test. However, both the grubs as well as the ESD test are seasonality unaware. And as some of the speakers have already mentioned, that data at Twitter, Netflix, Facebook, and other companies is highly seasonal in nature. So the challenge is really how do you find local anomalies, because you can always set thresholds to find global anomalies. You can say, mean plus 4 sigma or 3 sigma, and you can find global anomalies. But the challenge really is that in presence of seasonality, how do you find these local anomalies? And I'll walk you through some of the examples later in the slides. So let me quickly walk you through our approach. So first, as I mentioned, like presence of seasonality is a big challenge. The traditional techniques do not work off the shelf. So the key idea is very simple. There is this notion of in statistics called time series decomposition, wherein you can decompose any input time series into 3 components. One is the seasonality, one is the underlying trend, and the residual. So, and this is what I illustrate here. On the top, you see the what I show here is the raw time series. The second one is the underlying trend. The third one is the underlying seasonality, and the third and the last but not the least is the residual. So how does this time series decomposition help you in finding anomalies? Well, if you plot the PDF, which is the probability density function of the raw time series and the residual, which is what I show here on the slide. So the blue PDF corresponds to the raw time series, and as you can see, it is trimodal. So which makes application of the traditional test not meaningful, because all the traditional tests assume a normal distribution. But if you take the residual and if you plot the PDF, which is represented by the red curve, so as you can see, it is approximately normal. So which makes analysis of the residual time series using the statistical techniques like EST or any other out there in the literature. So we extract out the seasonality and the trend, and then we apply DSD. But this is not quite sufficient. So using the residual itself is not sufficient, and this is reflected here on the slide. So as you can see here, let's try this. So as you can see here, on the top I show the raw time series, and the second from the top is the underlying trend. So as you can see that corresponding to that anomaly, we see a false bump in the underlying trend, which induces these false negative anomalies in the residual. So this makes, so we want to avoid these false negative anomalies. So to cater to these, what we do is, instead of the underlying trend, we compute the median of the raw time series as reflected by the second row, and we subtract the median and the trend from the raw time series to obtain the residual. So as you can see, then in the modified residual, these negative anomalies have disappeared, and this is exactly what you want. So as most of the speakers earlier today have mentioned, that we really want a low false positive rate. You don't want your SREs to get up at 3 in the morning to figure out that hey, it was a false positive. So this is one way to remove the false anomalies induced by the underlying trend. So here what I show is the one application of our technique. So as you can see here, that on the left hand side, that our technique is able to capture even the local anomalies which you would not be able to detect using the Grubbs test or the ESD test. And of course you can find these global anomalies using our approach, but also you can find these local anomalies using the method I just described. So back in January, we open sourced a standalone R package corresponding to the technique I just described. It is available on GitHub. The package, as I mentioned, is seasonality and trend aware. It employs time series decomposition. So some of the key features of the package are the following. You can filter the anomalies. So here, for example, what I show here on the graph is that it shows 1 week of data, but only the anomalies corresponding to the last day are annotated. So you can always filter the anomalies for the last day or for last hour, so that your SREs can focus on only the most recent anomalies. Second, you can use the package to detect only positive, negative, or both kind of anomalies. In addition, you can also turn on a flag if you are interested in determining the expected values. And last but not the least, you can turn on a flag to do anomaly detection on longer range time series. So for example, if you have a business metric like tweets per minute and you want to analyze the last 6 months of data, so we came up with a novel technique based on piecewise approximation, and which lets you analyze longer range time series using the package. So you may wonder that why do we need this piecewise approximation? The challenge is that if you look at longer range time series, typically there is a prominent underlying trend which makes it very difficult to do anomaly detection. So for details, I strongly encourage you to have a look at our hot cloud paper we published in 2014. And since we open sourced this package in January, it has been pretty widely used outside Twitter in domains outside computer science like social ecology, sports, medicine, and so on and so forth. So it has been pretty satisfying after we open sourced the project. All right, so as I mentioned, the R package is good for finding anomalies in univariate time series, but typically given any service, for example, Heron, we have multiple metrics per instance. So the next natural question we asked ourselves was that can we leverage these multiple metrics to reduce the false positives even further? So to that end, what I'm going to talk about is still an ongoing work, that how can we leverage these multiple metrics in a very simple fashion so that we still need to be close to real time. There has been hundreds of papers which have been published in statistics, machine learning, where you can do multidimensional, multivariate analysis, but they are good for offline analysis. So can we come up with a technique which is really fast and still help us reduce the false positive rate? So our first attempt to leverage these multiple metrics is what we call as intersection analysis. There are essentially two applications of intersection analysis. First is with respect to host health, and the second one is with respect to service health. So what I mean by host health is you can have multiple processes on a single host. So the idea is to determine the intersection of the set of anomalies corresponding to each process, and then if we have if we do get a non-empty intersection set, then we can say with high confidence that hey, indeed there was an anomaly on this host, and this host is probably gone bad. The other application is determining the component health. So in a head-on topology, you may have different instances of the same component running on different hosts. So to be able to determine the component health, we determine the intersection of the set of anomalies of each instance. So we use our R package, which I just mentioned. We find the anomalies corresponding to each instance, and then we take the intersection of all these sets. If the intersection set is non-empty, then we can say with high confidence that probably something is wrong with the new release. So here, just like any other research venture, you need to validate that your hypothesis is correct or not. So when we applied intersection analysis to topologies in production, we were able to find real root causes of anomalies, and a couple of them are mentioned here on the slide. So we were able to identify container depths using intersection analysis, and we were also able to pinpoint spike in input using intersection analysis. And also, in some cases, we saw an increase in back pressure, which may happen because of high data traffic, which in turn leads to loss of metrics. So using intersection analysis again, we were able to find legitimate instances of increasing back pressure. Now, there are pros and cons with every technique. So what I mentioned just now, intersection analysis helps to reduce false positives, but however, it may have a high recall, where recall is defined by the ratio I mentioned here on the slide. Now, a high recall corresponds to a high number of false negatives. Now, there can be two potential sources of false negatives. One is that intersection analysis is highly susceptible to data skew, which may happen because of multiple reasons. There can be a collection issue, as one of the speakers mentioned earlier, that there can be a skew in the clock synchronization and so on and so forth. And moreover, intersection analysis is very aggressive. So either it follows an all or none strategy. That, for example, in case of component health, if and only if all the components of my instance have an anomaly, only then I'll report an anomaly. Now that's pretty aggressive. What if 90% of my instances have an anomaly? So we need to be able to factor that in. So the next idea we explored was to develop a confidence-based approach. So wherein we find the number of anomalies for each instance, and then we compute an average measure. That let's say if I have 10 instances of a component, then I'll compute a confidence measure for across all the instances. So this is not a all or none strategy. You want to find some average measure, but still this leads to underscoring. So what we came up with is this following approach, where using the formula I described here on the slide, you want to compute the anomaly score of an instance in a non-linear fashion. And the reason it is important is that you may have 10 instances of a component, and even if, let's say, 5 of them have gone bad, you may want to decide that, hey, this warrants some investigation. So not only when all the instances have gone bad, but a majority of them have gone bad, you may want to have your SREs look at that topology, that, hey, something may have gone bad. And that's why it is important to have a non-linear relationship between your number of anomalies and your confidence measure. So here, as you can see, that if your number of anomalies, normalized number of anomalies is 40%, your confidence level is still around 70%. So this is what you want. So going forward, so far I have described multiple models. How can we minimize false positives? Now keep in mind, just like any other problem in machine learning, that one model does not fit all. So here I illustrate a couple of metrics which neither have seasonality and nor have underlying trend. So applying the art package is not applicable for metrics like these. So it's really important. I would like to emphasize that, as some of the speakers have mentioned earlier, that the definition of an anomaly is highly contextual. So applying the art package for every metric is not meaningful. So it has to be, the application of the algorithm is dependent on the characteristics of the time series. And here you have, as I illustrate here, the algorithm I described will not work for metrics like these. So you need to do some sort of data transformation before you can apply, if at all, the algorithm I described. And I'm almost there. So to make the confidence-based approach even more robust, what we did was we introduced a notion of a weight. So instead of a vanilla average, we compute a weighted sum where the weight can be determined using local cross correlation, which accounts for the data skew. Or you can based on the domain knowledge, you can assign importance to the different metrics, like emit count and execute count have higher importance in case of storm or head-on topology. So depending on the domain knowledge, you can assign higher weights to certain metrics, and which will lead to a higher confidence measure for these corresponding metrics. So far I've been talking about finding anomalies on an instance level. You can abstract this at a higher level. You can find anomalies at the node level, where you can take the anomaly score of each instance on the node and just average it out. And so far we've been experimenting with it for topologies in production, and it seems to be working out pretty well. And last but not the least, as most of you already know, to be able to reduce false positives, it's also important that the anomalies reoccur at least k consecutive times, where k is parameterized, which depends on the particular use case. So just because you find a point in time anomaly, you don't want to flag an alert at 3 in the morning. So the anomaly has to occur k consecutive times, where k is parameterized, and only then you want to fire off an alert to wake up an SRE at 3 in the morning. So that's essentially summarizes what we've been building at Twitter. These algorithms have been deployed to find anomalies in the business metrics on a daily basis, in operation metrics, and more recently for finding anomalies in head-on topologies. So that's all I have. I'll be happy to take any questions you have. Yeah.
Is there a version of your R library available in another language?
No, right now we open source only the library only in R. You can, so there is a package called RPy, using which you can call a library from Python, but right now we don't have it in C++ or Java. I mean, again, just like RPy for Python, there are other libraries you can call R code from Scala and Java also.
So you can run the R version of your libraries in production environments, and just R is known for performance. So you have something that runs in a Swarm or Arun topology, or something for performance?
Yeah, well, so we use Mesos extensively, so this is deployed as a Mesos job. Yeah.
How are teams at Twitter adopting this knowledge?
So we have the R package I mentioned. It is used by at least over 10 different teams at Twitter. So depending on the use case, some want anomaly detection at the minutely level, some want at the hourly and daily level. So using the R package, you can set up email alerts, and depending on the use case, these alerts are sent to the different teams at different time scales. So like the Hadoop team is happy to find slow nodes every day. So we set up the job accordingly. Any other question? Thank you.